A chemical bond is not an invisible piece of string. It is an interaction among nuclei, electrons, and electric fields that can lower the energy of a group of atoms and make its arrangement more stable. So what is being held together is really a pattern of electron distribution and energy. Today, we will unpack 3 of the most familiar ways atoms connect. First, watch an electron change hands. A sodium atom usually has 1 valence electron, while chlorine is 1 electron short of a filled outer shell. When sodium gives that electron to chlorine, the result is a positive Na+ ion and a negative Cl ion. Their electrostatic attraction arranges many ions into a lattice, the collective picture of ionic bonding. When electrons are not fully transferred but shared between 2 atoms, a covalent bond forms. Each hydrogen atom brings 1 electron, and the 2-electron probability cloud gathers between the nuclei to make H2. That shared cloud attracts both positive nuclei while avoiding the intense repulsion of pushing them too close. Sharing does not always mean an even split. When the atoms differ, the cloud can lean toward one side. In a water molecule, oxygen pulls shared electrons more strongly than hydrogen, so the oxygen end is slightly negative and the hydrogen end slightly positive. Water therefore acts like a tiny electric dipole, and its direction affects how molecules arrange, dissolve, and attract one another. Polarity is not an extra pair of ions, it is an uneven distribution inside a shared bond. The metallic story is different again. Many metal atoms form a lattice, while their outer electrons are no longer tied to one atom and can move through the whole structure. A framework of positive ions together with this flowing electron C makes a metallic bond. Because electrons can move, metals usually conduct heat and electricity, and their layers can slide under force without immediately shattering. Bring 2 atoms closer and you can trace an energy curve. Too far apart, attraction has barely begun. Too close, repulsion between nuclei and electron clouds rises sharply. The bottom of the curve marks the neighborhood of the most stable bond length. Pulling out of this energy well takes energy, while forming a bond releases energy. A chemical reaction compares the total energy difference after bonds are broken and new bonds are formed. Ionic, covalent, and metallic bonds are not 3 differently colored strings, they are ways electrons organize across different scales and structures. They help determine whether a crystal conducts, whether a molecule bends, and how a substance melts, dissolves, and reacts. Next, we follow an ordinary-looking but extraordinary molecule. Why is water so special? Polarity, hydrogen bonds, and life will connect the answer. See you next time.